Hello, I'm Julia. This is my piece of number 5. Okay, so we start in 32 lib, and then step number 4, I loaded up movies, so I opened up the movies dictionary as a file, and I read the dictionary, and then for every row in the reader, the ID is just like where I index into the row, into the ID, and then I index into movies with the ID, and then I get pull out title, year, row, and stars. Stars is a set because I want only unique values in there because I don't want duplicates people. Um, and so, yeah. And then I load up my movies dictionary. And then for the second part, it's building the names dictionary. So basically, I look through every ID, person ID, and people dictionary, and then I pull out their name, which is how I basically just index into people with their ID, with their name, and I lowercase everything. Oops. And then if the person name is not in my names dictionary, which at first none of them will be because it's empty, then I create a new key with their ID, like with the person's name, and then their ID as a set because I don't want to deal with duplicates yet. But then else, if there is a duplicate name, then I will dot add to the I will add their ID to the previous set ID in names. So that's how I deal with duplicates. And then next I move on to step number 7. Um, so I look through every single ID in people and then I index into people with their ID and then into visited and then I set it all to false because I haven't visited any of them yet at the beginning. And then I initialize my start node. Um, well, I make my start node first, and then there's no parent, there's no action, no movie ID because it came from nothing. It's just starting, and then I add my start node to the frontier first to look through, and then while my frontier is not empty, I'm going to remove the last node that I added in a depth first search. Um, to look through. And then if my person ID, node.state is person ID, is equal to the person I want, like who I want to end up with, then I want to return the path. So I make a path list. And then while the previous node that I came from is not nothing, so while it's not the start node, then I'm going to add the node to this current node to my path. And then I want to like retrace my steps. So now the node is equal to the node that it previously came from, the node.parent. And then my path, I'm going to add, at the end, I'm going to add my start node to the path. And then I'm going to reverse my path because I wanted to make it look like I like went down, not like retracing my steps. Now I want to like make it look like I went down this path. And then I want to return the path. But if you haven't found the person that you want to look for yet, then you have to set this person's ID to you have visited it and to like add more nodes to your frontier to look through. I basically made a function like find neighbors. So I basically you input the person ID and then neighbors is a list for movie ID in which you index into person, people, ID, movies, and then all their co-stars in the movie, same movie ID, and then stars. Um, if the person ID is not equal to the co-star ID, then that means this is someone that they starred in the movie with, and so you want to add this person to neighbors, and this returns like a list of all the people that like a certain person has starred with in this particular movie. Um, if people if you haven't visited this person yet, then you want to add this node to the frontier to look through later. Um, So yeah, and you're gonna look through this right away in a depth first search. And then let's check. Let's make sure it's a depth. Yeah, DFS, stock frontier. I mean, this and this works. Okay, step number 8, I made Q frontier, which I basically inherit all of stack frontier's functions, but I overwrote remove because in a um because I want I want to like I want to look through the first. node in the frontier rather than the node that I just added. Um, and this allows me to not go through a single path all the way down and then finally find out it's a dead end. I get to check everything first at the same time, and then be able to find my goal person faster. Um, so the node is now the first one in the frontier, and then and in the frontier, I get rid of everything except for the first node, and then I return the node. And then let's check it. Mm-hmm. First search. Demi Moore Mandy Patinkin. Yes, lovely. Okay, okay. Now I'm gonna run it with Emma Watson. I should get not connected, and I'm gonna do BFS for this one. Yeah, Demi Moore, Emma Watson. Let's do 9, 1, 2, 3, 4, 5, 6. Not connected. Yes, works. Um, and then in step 9. Okay. Uh, so basically for the DFS, it was running way longer than a minute. And so I asked AI to help me make it more efficient. And basically what it said was every time you're checking if the person ID, like if you haven't visited this person yet, you should like filter whether or not you add it to the frontier. So this is where the efficiency, this is everything I wrote, and this is where the AI starts. So your neighbor is equal to this node, and then if the person ID, you check here. You check if the person ID is equal to the person that you want, then you will reconstruct the path immediately. Um, but if the person isn't, but you just add this to the frontier. Um, and I assume that, and I know that this is going to be faster because you immediately check. You don't have to like add it to the frontier and then you go through every single step to check. This way you just check immediately and it's going to be faster. And when I checked it, it did run faster. And yes, let's go. Let's do a BFS first because I know this is faster. On the big data set. Data set large. Lovely. Step 9 PY. On Kevin Bacon, Marlon Brando. Loading the big data set. Okay. Kevin Bacon. 2 degrees of separation. Yay! Yummy! And I believe this is correct. 2 degrees. Yes. Good. And then let's do DFS. Hopefully this is not too long. Hopefully. So the data set. Okay. Kevin, bacon. Yay! That was fast. So yeah. It's not exactly the length that this uh yeah, this said, but it said it would be different. So, yeah. Um, thank you.